Okay, let's unpack this. We're diving into a stack of source material today, and it really is like a crash course in one of the most fundamental forces out there, universal gravitation.
It really is. And these sources, they're great because they give us the whole picture,
Yeah.
blending Newton's mechanical genius with all the massive cosmic consequences we see today.
Yeah, we're talking everything from like how they first figured out the Earth's mass in a lab all the way to black holes.
Exactly. The geometry of black holes, even.
So our mission today really is to give you, the listener, a kind of shortcut. We want to pull out the core mathematical rules
The really key ideas.
and show you how those rules are, well, responsible for pretty much everything. Tides, planets being discovered.
It's amazing stuff. And what's fascinating is this foundation, it's only, what, 350 years old, roughly?
Yeah.
And yet it's still the bedrock for so much classical physics. So we'll dig into the what and the how of gravity, and then, yeah, jump straight into the so what for the universe.
And before we jump in, just want to highlight something from the sources. They acknowledge the contributions of physics teacher Hakivavelli Tarun,
Oh, yeah, that's right.
which is just a nice reminder of how this fundamental knowledge gets shared and passed down. A really great example.
Definitely. Okay, so where do we start? Got to be Newton, right?
Has to be Sir Isaac Newton.
Yeah.
And the core idea he gave us is, well, it sounds simple at first. Every bit of mass pulls on every other bit of mass.
Simple idea, but he didn't just say it. He quantified it, put math to it.
Exactly. And that gives us the law of universal gravitation. The formula itself, 12T Frec M1 Miller 2, it kind of tells the whole story, doesn't it?
It does. The force of attraction, that's $5, and it depends on, well, two main things.
Right. First, the masses, $1 and $2 The force is directly proportional to the product of those masses, which makes sense, right? More stuff, more pull.
Yeah, intuitive. Double the mass of one object, you double the force between them. Simple enough.
But then there's the distance part.
Yeah.
And this is where it gets maybe a bit less intuitive.
Ah, yes. The killer catch, as you called it earlier. The force is inversely proportional to the square of the distance between their centers. $2.
Okay, why is that squaring so important? Why the inverse square?
Because, well, it means gravity gets weaker really fast as you move away. It's not just a linear drop-off.
Right.
Think of it like spray paint from a can or light from a bulb. As it spreads out, it covers a larger area.
Okay.
If you double your distance from the source, that light or paint is now spread over 4 times the area. So its intensity, or in our case, the gravitational force, is only 1/4 as strong.
Ah, I see. So triple the distance.
And the force drops to 1/9. It fades out dramatically. That's why, the gravitational pull of Jupiter is huge, but we feel the Earth's pull infinitely more. Distance matters a lot.
Gravity's powerful up close, but distance is its weakness, its kryptonite, as the sources put it.
Perfectly said. Now, what about that little letter $di in the formula?
Right, the universal gravitational constant. Newton knew the relationship was proportional, right? He knew force scaled with mass and distance in this way.
Exactly. He knew $5 was proportional to Frackman 1's UDO, but he couldn't figure out the exact number, the conversion factor needed to make it an equality.
The cosmic adjuster. The number that tells us precisely how strong gravity actually is.
And it turns out dollars is incredibly small, like really, really tiny. The value is roughly $6.67 times 1011 in the standard units.
Wow, okay. That's minuscule.
It is. And that tiny number is why gravity feels like such a weak force in our everyday experience. Unless you have a massive object like a planet involved, you don't feel the gravitational pull between, say, 2 chairs in a room.
It's too weak without huge mass.
Precisely. Which makes what Henry Cavendish did in 1798 even more impressive.
Yeah, this was, 70 years after Newton died?
That's right. He set out to actually measure this tiny force and figure out dollars.
How on earth did he do that?
Well, with incredible precision. He used something called a torsion balance. Imagine hanging 2 small lead balls on a wire, very delicately balanced. Then bring 2 huge lead spheres close to them.
Okay.
The tiny gravitational attraction between the small balls and the big spheres causes the wire to twist, just a minuscule amount.
And he measured that twist.
He measured that tiny twist, and because he knew the masses of the balls and spheres and the distance and how much force it took to twist the wire, he could calculate $d. It was unbelievably meticulous work.
Wow. And by finding G,
He could plug it back into Newton's law, along with the known acceleration due to gravity on Earth's surface, and essentially he weighed the Earth. for the first time.
He weighed the world. That's incredible.
It really was a landmark experiment.
Okay, let's go back to that inverse square law for a second. If distance matters so much, does my weight actually change measurably if I go from, say, sea level to the top of a mountain?
Technically, yes, measurably, barely. But yes, it does change. And this brings up a really important distinction that the sources make: mass versus weight.
Right, they aren't the same thing.
Not at all. Your mass is the amount of matter, the stuff you're made of. That's constant wherever you go. Earth, moon, deep space. Same mass.
Okay.
Your weight, though, is the force of gravity acting on that mass. And since force depends on distance, according to Fg 1 millitou, your weight does change depending on where you are.
We usually just feel it as the ground pushing back up on us, the support force.
Exactly. That's what a scale measures. And that force is strongest for us right here on the Earth's surface.
So the sources say gravitational force is maximal at the surface. What happens as you move away?
As you move outward, further from the Earth's center, the force decreases according to that inverse square law. So if you weigh, say, 1 Newton right here.
Which is a unit of force, yeah.
Right. If you go to a distance that's twice the Earth's radius from the center, so 1 Earth radius above the surface, your weight would drop to only 1/4 of a Newton.
Okay, makes sense. Inverse square. But what about going inward, like down a hypothetical tunnel towards the Earth's core? This part was fascinating.
Yeah, this is counterintuitive. As you go deeper into the Earth, the gravitational force pulling you towards the center actually gets weaker.
Weaker. Why?
Because now there's mass above you as well as below you. The shell of Earth mass that's further from the center than you are is now pulling you outwards, partially canceling the pull from the mass below you.
Ah, okay, so the net pull toward the center decreases.
Exactly. Until, if you could reach the exact center of the Earth, the net gravitational force would be 0. You'd be pulled equally in all directions by the surrounding mass.
You'd be weightless at the center.
You would. Which leads us nicely to that common misconception about astronauts in orbit.
Right. People see them floating and think zero gravity.
Yeah, and that's just not right. Gravity is still very strong up there in orbit, maybe, like 90% of what it is on the surface.
So why are they floating?
They're experiencing weightlessness because there's no support force acting on them. They and their spacecraft are in a constant state of free fall around the Earth. They're perpetually falling, but also moving sideways so fast they keep missing the ground.
So it's not zero gravity, it's zero apparent weight because they're falling.
Precisely. Continuous free fall. That's the key.
Okay, let's scale this up. We see the inverse square law, this effect of gravity, playing out visibly with ocean tides, right?
Absolutely. Tides are a direct, everyday consequence of gravity acting differently across the Earth.
How does that work?
Well, think about the moon pulling on the Earth. The side of the Earth closest to the moon gets pulled slightly harder than the center of the Earth.
Right.
And the center of the Earth gets pulled slightly harder than the far side. This difference in pull, this stretching effect, is what causes the oceans to bulge out on both the near side and the far side relative to the moon.
Right. The differential gravity again.
Exactly. And what's really interesting here, something the sources highlight, is the role of the sun versus the moon.
Yeah, the sun's way more massive, but the moon causes bigger tides.
That's right. The moon is about 2.2 times more effective at raising tides. And again, it comes back to distance and the inverse square law, specifically the difference in distance.
How?
Because the moon is so much closer, the difference in its gravitational pull between the near side and far side of Earth is much greater, proportionally, than the difference in the sun's pull, even though the sun's overall pull is stronger.
Ah, so the stretch from the moon is more significant because it's closer.
Exactly. It's that differential force that dominates the tides.
That really shows the power of the formula, and maybe the most, I don't know, dramatic historical example of that power was the discovery of Neptune.
Oh, absolutely. That story is just, it's a perfect testament to the predictive power of Newton's laws.
This was back in the 1840s.
Yeah. Astronomers had been tracking the planet Uranus for a while, and they noticed its orbit wasn't quite right. It was wobbling, essentially, deviating slightly from the path predicted by Newton's laws, considering the pull of the sun and the known planets.
So something was off.
Something was off. But instead of thinking Newton's laws were wrong, they thought, maybe there's something else out there. Another planet, unseen, whose gravity was tugging on Uranus.
That's a leap of faith in the math.
A huge leap. And two mathematicians, John Couch-Adams in England and Urbain Le Verrier in France completely independently sat down and did the calculations.
They used the observed wobble in Uranus's orbit.
And Newton's law of gravitation to figure out where this hypothetical perturbing planet must be located to cause that specific wobble.
They calculated the position of a planet they couldn't see, just based on its gravitational effect.
Exactly. Leverrier was particularly confident and sent his calculations to the Berlin Observatory. He basically said, point your telescope right here tonight. And they did. And within an hour, they found Neptune, almost exactly where Leverrier predicted it would be.
Wow. Just wow. That's incredible. All from FG Fracare and 1 Militubati.
It's arguably one of the greatest triumphs of theoretical science. It just cemented the power of Newtonian mechanics.
And if we push gravity to its absolute extreme, we get black holes.
Right. That's where gravity isn't just dominant, it's absolute. It wins.
This happens when a really massive star runs out of fuel and collapses under its own gravity.
Yes, it collapses catastrophically. If it's massive enough, it can collapse down so much that the escape velocity from its surface becomes greater than the speed of light.
Meaning nothing, not even light, can escape its pull.
Correct. And the boundary where the escape velocity equals the speed of light, that's called the event horizon, the point of no return.
And the inverse square law still holds, even in these extreme conditions.
It does, and it highlights how intense things get. The sources mention, if you could somehow compress a star or any massive object, reducing its radius by half, the gravitational pull at its new, smaller surface would become 4 times stronger, quadrupled. That incredible density is what creates the inescapable pull of a black hole.
So we have these incredibly powerful foundational laws from Newton. They explain so much. But science didn't stop there, right? The sources hint at the evolution of thought.
That's right. It's crucial to remember Newton gave us this picture of gravity as an attractive force acting between objects across space.
Pulling things together.
Yeah. But then, fast forward to the early 20th century, and Einstein comes along with general relativity. And he offered a different perspective.
A fundamentally different way of looking at it.
Completely. Einstein described gravity not as a force, but as a consequence of the geometry of space-time itself.
Okay. Break that down a bit.
Think of space-time as a fabric. Massive objects like planets and stars create curves or dips in this fabric.
Like putting a bowling ball on a trampoline.
Exactly like that. And other objects like smaller marbles or even light rays moving near that bowling ball just follow the curves in the fabric. They're not being pulled by a force, they're just moving along the warped geometry of space-time.
So gravity is the shape of space-time, essentially.
In Einstein's view, yes, it's a geometric effect, not a force transmitted across space.
That's a huge conceptual shift. But Newton's laws still work, right?
Yeah.
Most things.
Oh, absolutely. For almost everything we deal with, from launching satellites to calculating tides to predicting planetary motion, Newton's law is incredibly accurate and much, much simpler to use than general relativity. Einstein's theory really only becomes necessary in very strong gravitational fields, or when dealing with things moving close to the speed of light, or for extreme cosmological precision.
So the classical rules remain vital.
Indispensable. And this evolution from Newton to Einstein, it really shows how science builds on itself. And it relies on people passing that knowledge down effectively. Like the teacher mentioned in the sources, hockey veli turum.
Right. Ensuring those foundational principles are understood is key.
It absolutely is. Because whether you're using Newton's formula or Einstein's field equations, understanding those core concepts of mass, distance, and how they shape the universe is fundamental.
So for you, the listener, what this deep dive really shows is that these mathematical rules, whether classical or modern, are the tools we use to understand everything from why you stick to the Earth to how entire galaxies hold together.
They're the language the universe seems to speak, at least when it comes to gravity. And we're still learning to decipher all of it.
Okay, so wrapping up this deep dive, we really covered some ground. We unpacked the core math of gravitation, FG frac M1 militude.
Yep. Saw how Cavendish cleverly used tiny forces to weigh the entire Earth, which is just brilliant.
We clarified why astronauts float their falling, not in zero-G, and we relived that amazing moment when a wobble in Uranus's orbit led straight to finding Neptune.
A triumph for the predictive power of the law.
We managed to get through quite a bit, hopefully giving you a solid, quick understanding.
And maybe, just maybe, a provocative thought to leave you with, thinking about stories like Neptune. It does make you wonder, doesn't it? Are we sometimes too quick to sideline classical theories like Newton's just because we have newer, perhaps more complete ones like general relativity.
What do you mean?
Well, if a foundational idea like universal gravitation works so well for so much of what we observe, explaining things with such incredible accuracy for centuries, could there still be unseen implications? Or maybe applications of it, perhaps in combination with newer ideas that we just haven't fully grasped yet?
Even within the framework of general relativity?
Perhaps. Or maybe aspects of the Newtonian view that still hold deeper truths than we currently appreciate. It just suggests we shouldn't discard the old tools entirely, even when we get shiny new ones. They might still have some undiscovered uses. Something to mull over, anyway.
Definitely something to think about. The enduring power of foundational ideas. Thank you for joining us for this deep dive into universal gravitation. We'll see you next time.